So we'll look at our electricity unit assignment that we just collected this morning here, starting with question number 1, which was, as it turned out, a repeat. That repeated, I think, number 16, something like that was ended up repeating. So I ended up counting it the first time and not counting it the second time. I think it ended up being out of 25. Number 1 says, one of the differences between the phenomena related to Newton's law of universal gravitation and Coulomb's law is that only one allows for a force of repulsion. Of course, Coulomb's law can be attractive or repulsive. Gravity is only attractive. Number 2, the electric field at a point midway between the particles is what? We don't know the values of the charges here. We do know the value of the distance, but we don't know the value of the charges here. So this might end up being a variable value changing type question. Well, let's see. Here's our point midway between. We have a field caused by number 1 that goes to the left. E1 goes to the left because it goes toward the negative. And we have a field caused by number 2 that goes to the left because it goes away from the positive. Does that make sense? All right, if they're both to the left, which way is our net field? To the left. So the answer is going to be B, towards the left of the page. Now, it tells us that this is 3 times the charge of this one. So if we had, and we don't, but if we had number 2 going to the right, which way would the field be then? Would we know which way the net field was then? Yes, we would. Yeah, Julia? It would still be to the left, and how do you know that? Good, because charge 1 is greater than charge 2, therefore the field caused by charge 1 is going to be greater. Now, if I said, where is the point where the field ends up being 0? I wouldn't expect you to calculate that because that's a crazy hard math question, right? But where approximately would it be? If the field was 0, would it be closer to number 1 or closer to number 2? That is, if the field caused by number 2 is to the right. So let's pretend for a second that number 2 was a negative and the field caused by number 2 is to the right. Where would we have to be for the field to be 0? In the middle, to the left, or to the right of the middle? To the right, yeah. It would have to be over here somewhere because this bigger charge creates a bigger field, so we'd have to have a bigger distance to kind of compensate for that. All right, good. So the answer to the question as asked was B, toward the left of the page. Both of those questions were really well done, by the way. Number 3. The number of excess electrons given to an ink drop. Lots of information up here, but all that matters when we're looking for a number of electrons is what? What do you got to do? What do you got to do? If I'm looking for the number of oranges in a bag, I'm going to take the total mass of the bag of oranges and divide it by the mass of 1 orange, right? If I want to find the number of electrons, Shailene, what am I going to do if I want to find the number of electrons? Yep, the total charge divided by the charge of 1 electron. So the number is equal to Q total divided by Q, the charge of 1 electron. So what is it? Negative 1.51 times 10 to the minus 13 divided by negative 1.6 times 10 to the minus 19. And we get an answer of 9.44 times 10 to the 5 when we do that. Right? That was well done as well. I think. Let me just check here. Yeah, that was pretty well done as well. Number 3, very well done. The deflection plates are 0.1 millimeters apart. Almost everybody caught that, the fact that it's millimeters, and we're going to convert that to meters. There's a potential difference of 120 volts across, and what's the electric field between the plates? Pretty straightforward if we get the unit conversion there, right? What are we going to do to solve for this, Maddie? Yep, so let's make the distance there 0.100 times 10 to the minus 3 meters. Or you could just divide by 1,000 and move the decimal place. I don't like doing that because when I already have a 0 decimal something, I find when I start moving the decimal over, I find that I mess up on that. So I usually just tack on a 10 to the minus 3. But whatever works for you there, okay, as long as you do the conversion. What do we do after we got delta D here? Good. we do delta V divided by delta D. This is my producer equation for a uniform electric field. And since that's what I've got here, a uniform electric field between these plates, and that's what I'm going to do. When I do the division there with this number for distance, number 3 gives me A, 1.20 times 10 to the 6 newtons per coulomb. Notice they're all 1.2 zeros. So basically what they're saying is, if you forget to do the conversion or you do the conversion wrong, you're going to get one of these answers. So even when you know what you're going to do, E is equal to delta V over delta D, even when you do it wrong, you're going to get one of these answers. Basically, this question isn't testing your knowledge of electric fields so much, because you have to do E is equal to delta V over delta D to get one of these answers. It's testing, do you know how to convert? Do you know that you have to convert, and how to convert? All right, number 4. As the charged ink drop I1 moves through the deflection plates, it experiences a force with, well, remember that we had 3 equations for electric field. E is equal to kq over r squared. Don't forget to put the arrow over that. Don't want to get it mixed up with energy. E is equal to F over Q, and E is equal to delta V over delta D. On your data sheet, they're listed right below each other just like this. Just like this. Okay, on your data sheet, when you get your unit test tomorrow and on your diploma exam, it might be a good idea to circle the first 2 and the last 2, reminding us that we have these things that are in common here. So what are we going to do here now to find this force? We already used the last equation because it's a uniform field, right? What other equation is valid with this equation? E is equal to F over Q, right? So let's try that. Rearrange this to solve for F. We get Q times E. Multiply the charge by the electric field strength that we just found. And when we do that, we get an answer of D, 1.81 times 10 to the minus 7 newtons. 5, good question here. To cause the ink drop I1 to follow the path shown, the deflection of the electric field, or the direction of the electric field, must be which way? Let's go back here. These negative particles are moving, like before they enter these plates, which way are these particles moving? They're moving to the Blake? To the right. So the velocity is to the right. Now, what kind of particles were they again? Positive or negative? Negative. Okay, if we have negative particles, regardless of which way they're moving, negative particles will always experience a force, which way? Opposite or against the field, right? I'm positive the force is with the field. I'm positive particles, the force is with the field. But if you get a negative particle, the force is against the field. Which way is the force acting on this particle to make it kind of curve upwards here? Which way is the force? It's toward the top of the page, right? If the force is toward the top of the page and it's a negative particle, which way is the field going to be? Yeah, the field's got to be down. The field's got to be opposite to the force. Now, that was a positive particle, and the force was up toward the top of the page. Which way would the field have been? Up toward the top of the page. I'm positive the force is with the field, but only for positives. It's opposite to the field for negatives. So it looks like our field is going to be downwards here, toward the bottom of the page. The answer is A, and you guys did well on that one again as well. 2 conducting spheres have identical surface areas. 2 charges here. A and B are brought into momentary contact, separated by 2.5 centimeters. Why are they telling me they have identical surface areas? Why are they telling me these things are the same spheres? Yeah, Taylor? Right. When they touch together, they're going to balance out. We know they touch. We know they're going to balance out. And then they're separated to a distance of 2.5 centimeters. Let's circle this, this, and this. Tomorrow when you do your test, like circle those things, right? You're allowed to write all over your test. You should draw attention to those things by circling it in red or highlighting it or something, right? Don't forget those little things, because those are the little things that often cause us to, you know, we're not going to fail a test because of unit conversions. But it might make the difference between an 80 and a 60, conceivably, right? If we really mess up on them. But even the difference between an 80 and a 72. Like, that's a big difference. And you don't want to lose those points just because of silly unit conversion issues. After contact, what's the charge on sphere A? All right. It's going to be the same as sphere B. Taylor, a second ago, I said, I think it was Taylor, right? Yeah. So they balance out. That's where they're telling me they're identical surface areas. So what are we going to do to balance them out? Queenie, what are you going to do here to balance these guys out? How do you figure what the average of those is? What they balance out to be? Yeah, add them up, divide by 2. 4.5 plus negative 2.4 divided by 2. And then, of course, it's times 10 to the minus 6. So what do we get there? 2.1, 1.05 times 10 to the minus 6 coulombs, or 1.05 microcoulombs. So my answer for that one is A. And again, well done. So far, so good. Doing really well so far. Number 2, what's the magnitude of the electric force exerted by sphere A on sphere B after contact? The key here is recognizing that after contact the charges are different, but we just found what the charges are. Uh, 1.05 microcoulombs, 1.05 times 10 to the minus 6. What was my distance there? What's going on here? Why isn't that going? There we go. Distance is 2.5 centimeters. So we're going to say 0.025 meters. Don't forget to square that because I circled it in red, right? What have I done there with a 1.05? 1.05 squared? Isn't it k q1 q2, not k q1 squared? It ends up being the same thing, right? Because it's the same charge. So I just figured, yeah, you know what, I'll save myself a couple keystrokes in my calculator. Okay? But whatever, right? If you want to times the two numbers and plug them both in, that's fine, doesn't matter. When we do that, we end up getting 15.9 newtons. And we're not asked to express that in scientific notation, so we just literally write it as 15.9. If it was scientific notation they were asking us for, they would say 1.59 times 10 to the 1, probably a 1591. 7, a positively charged object is moved from position M to position N. As a result of this change in position, the, good question. Good question. Does the force increase? What do we know about the electric field between these plates? Goes upwards, right? From positive to negative. What does the parallel nature of these electric field lines tell us? Yep, Laura? Right, it's a uniform field. A uniform field. And if it's a uniform field, we take that experiencer equation, the charge doesn't change, the field doesn't change. What about the force? Doesn't change either. So the field is the same here as it is here, as it is here, as it is here. The force must be the same here as it is here, as it is here, as it is here. So the force doesn't increase, it stays the same. The force doesn't decrease, it stays the same. The potential energy, if a positive is going away from positive, is it going to speed up or slow down? If a positive is being repelled by the positive and attracted to the negative, like is happening here, does it speed up or slow down? It speeds up. And if it speeds up, what happens to the potential energy? It's like a car going which way? Down a hill, right? Car speeds up down a hill. What happens to the potential energy of the car as it goes down the hill? It decreases, yeah. So the answer is going to be D. The electric potential energy of the object has decreased. Lots of information here. We've talked about this before. When you get a full page of information, skim it, skim through it. If anything stands out to you when you're skimming through it, then make a little note about it, but don't sweat that, okay? Once you read the question or questions that go with it, then you want to go back and look at it in a little bit more detail, okay? Now, if you do happen to be skimming through it and you come across a word that kind of is like, that's kind of like, I don't know if that makes so much sense to me, like draw attention to that so that you can kind of, when you go back to it later on, look at that word in context a little bit more and try to figure out what it means, right? But that first time through, just kind of skim and see what you end up with. See what the question ends up being. The minimum electric potential difference required to accelerate the helium-hydrogen ions from rest is, I'll tell you what, there can only be one answer here. There can only be one answer here. How come? Like, we could eliminate 3 right away. How come? Yeah, Laura? Well, what are we looking for here? Potential difference? What units are potential difference measured in? Volts? There's only one that has volts there, or megavolts. Right? The answer has to be C. Has to be. Because it's the only one that has proper units, right? Now, let's figure it out, though, because we don't want to rely on that. Maybe next time there's other units, there's other options that are in volts as well. What do you do when you're looking for the potential difference required to accelerate an ion, a charged particle? Every time a charged particle speeds up, what should you think? What should come to mind every time a charged particle speeds up? Well, that's like a car doing what? Going down a hill. So let's treat it that way, as a car going down a hill. We're going to say EI equals EF. What kind of energy does the car have when it's at rest at the top of the hill, McKenna? What kind of energy does the car have when it's at rest at the top of the hill? Potential energy, MGH, right? What kind of energy, whoops, should be initial. What kind of energy does the car have when it reaches the bottom of the hill? Kinetic energy, right? Now we're going to replace MGH with QV, because we're not talking about gravity, we're talking about electric potential. And that's what we're looking for, right? The initial potential, which ends up being the same as the potential difference. Okay, what do we got here? Helium hydrogen ion. Okay, HEH plus. So the charge is plus 1, or 1 times the elementary charge, 1.6. If it was, what is one that has 2 plus? Who's in chemistry? Let's go with oxygen, because it's 2 minus, I think, isn't it? Okay, oxygen 2 minus, what would the charge of that be? Negative 2 times the elementary charge, or negative 3.2 times 10 to the minus 19 coulombs. So He plus has a charge of 1.6 times 10 to the minus 19 coulombs. We're looking for VI. Oops. We don't know the final speed of this helium hydrogen ion, but we do know its kinetic energy just before the collision, after it's accelerated, is 3 mega electron volts. So we're not going to actually use this 1/2 mv squared. We're just going to say it's EK, right? The final energy is EK. Now we do have to convert mega electron volts to joules, so we're going to say 1 eV over 1.6 times 10 to the minus 19 coulombs. Where did I get that from? Where did I find that conversion? 1 eV is equal to 1.6 times 10 to the minus 19, Isaac? Yeah, it's on the left-hand side of the data sheet. That's equal to 3.00 times 10 to the 6 eV over x. Sorry, that should be joules, not coulombs. So we solve for this, solve for x. X goes up, the 1.6 goes up. We end up getting 4.8 times 10 to the minus 13 joules. So my final kinetic energy in joules, 4.8 times 10 to the minus 13 joules. Now we divide by 1.6, and lo and behold, we end up with 3.00 times 10 to the 6 volts. So it ends up being the same number, but that would not be the case if it was, say, a proton or an alpha particle. Well, it would be if it was a proton, actually. If it was an alpha particle, we would have a different number than my EVs. So don't assume just because you saw 3 mega electron volts that the answer is going to be 3 megavolts. Okay, it's a coincidence because we used electron here. So answer for number 8 is C, and that one wasn't quite as well done. Probably because of the units messed some people up. Okay, does it make sense now, though, guys? Everybody understand that conversion of electron volts to joules? I don't know. I'm not sure if you have to do that on the test tomorrow or not. But I told you guys going into this assignment that that's not normally something I do quite yet. If we do happen to see electron volts on the test tomorrow, and you want a little bit of help on the conversion there, I can give you a little bit of help on the conversion tomorrow. Okay, not down the road, but tomorrow I can. Okay, number 9. The electrostatic force of repulsion of the alpha particle and the proton, each other immediately after the collision, is what? Well, what do we got here? After the collision, they're going to be immediately after the collision. The distance between them is going to be this distance, 8.00 times 10 to the minus 11. So if we want to find that force, then all we're going to do is say, use the charge of the alpha, 3.2, the charge of the proton, 1.6, and R is going to be that distance between the bond, 8.0 times 10 to the minus 11. So why is it that number? Why is it the distance? Why is it the length of the bond? Why are we using that as our distance between the alpha particle and the proton? Yep. Yeah. Yeah. When they break up, like the instant they break up, that's the distance they are away from each other, the length of that bond. And that's when we're trying to find the force, is when they break up. Or immediately after the collision. 10. As the alpha particle and proton move apart, the force varies. It's going to be inversely, right? Inversely with the square of the distance between the particles. For number 9, it was B. 7.19 times 10 to the minus 8. Right, if F is equal to KQ1 Q2 over R squared, then F varies directly with Q1, and it varies directly with Q2, and it varies inversely with the square of the distance. Bottom of a thundercloud usually becomes negatively charged. Before the lightning strikes, the charge on the ground directly beneath the thundercloud will become what? So if this is negative, down here, the ground is going to become, well, it's neutral, right? But what happens as a result of this negative charge up here before the lightning strike? What's it going to do? It's going to become positive, you're right, but why is it going to become positive? Not so much the positives getting pulled up, but the negatives getting pushed down, right? So these negatives all go down here somewhere, leaving the ground positive. And what do we call that? Charging by, Logan? Charging by, what is it? Induction. Good. Charging by induction. So it becomes positive by induction. The answer is A for that one. Very well done question, as was number 12, which asks us for the charge on the top of the tree. Okay, as these electrons come down from the cloud, the charge on the top of the tree is going to become what? Like the tree is effectively neutral. When you get a bunch of negatives, what happens? It becomes negative by this one's conduction, because we're transferring charge. Even though it's not actually touching, we're transferring charge there. Right, Thomas? Yep. So we're going to say it is negative by conduction. The answer is B. 13. Oh, no, number 3. Which you guys did a good job on, actually, for a tricky question. The magnitude of the electric force. Look at what's happening here, guys. We want to find an electric force. Like, our temptation is to say F is equal to KQ1 Q2 over R squared. Listen, if I was in grade 12 and I saw a question like this for the first time, that would absolutely be my temptation. But I couldn't do it that way because I don't know anything about the distance, and I don't know the charges and whatever. Right, Thomas? I don't know any of that stuff, so I can't do that. Well, then I try F is equal to Q times E. That's my experiencer equation, right? This metal sphere experiences a field, and I can solve for the force that way, except I don't know what Q is, I don't know what E is, so that's not going to be helpful either. But then I realize, they gave me a bit of a break actually on this one, make it a little bit easier for me. Then I realize that I have an electric force pushing the metal sphere to the left. I have a force of gravity pulling the metal sphere down. And I have a string, we'll call it Fs for the force of the string, pulling it up like this. Now, if I've got something in equilibrium, something that's not moving, then the forces have got to balance, right? That means if there's a force to the left, the electric force, then there's got to be a force to the right that balances that. If there's a force down, then there's got to be a force up that balances that. So in other words, the x component of this diagram, the x component of the force of the string, is equal to the electric force. And the y component has got to be equal to the force of gravity. Right? Gravity balances out the y component. The electric force balances out the x component. They do a diagram for me here. They say gravity is down. The electric force is to the left. I don't like this diagram, actually. That's not a vector diagram, is it? I just noticed that. What's wrong with that as a vector diagram? They got to all be drawn head to tail, right? Except the resultant, which is drawn from start to finish. The resultant should go this way, right? That is not a vector diagram. Although, in the end, the trigonometry is still going to work for us. You want to draw as a vector diagram, what we really should have probably is this. X, Y, and Ft. All right, anyways, we have the angle here 78 degrees. We know that the force of gravity acting downward is m times g. So we're just going to say tan 78 degrees is equal to opposite over hypotenuse. All right, when we do the math there, it works out to be 4.17 times 10 to the negative 5. That's a tough question, but it's not as tough of a question as if they didn't give me that diagram, that so-called vector diagram. It's not really a vector diagram. How do we express this? A, B, C, D? $4.175, right? 4.175. $13. Getting there, guys. The direction of the electric force experienced by the charged glass bead as it falls through the region. It's a negatively charged glass bead. We got a field that points this way from positive to negative. Which way is the force? Nathan, look up here. Which way is the force on a negative particle when there's a field to the left? Which way? Yep. It's opposite to the field, right? Good. I'm positive the force is with the field. I'm positive the force is with the field. But for a negative particle, the force is against the field. So the force, the electric force here would be to the right. And that was well done. 14 was good, although not quite as good. Which of the following rows matches the type of motion exhibited by the glass bead as it travels through the region between the parallel plates of the uniform, or parallel plates of the direction of that motion? Listen, you got to understand what this stuff means. Uniform accelerated motion means acceleration, constant acceleration. Uniform motion means constant velocity. Let's look at up-down first. Up-down. As this bead falls down, what happens to it? Downwards. It speeds up. It accelerates, right? So in the downward direction, we would say that it was accelerated motion. What about horizontally here? This one's trickier, although it doesn't have to be. Does it accelerate horizontally as well? Or does it move at a constant velocity horizontally? What did we just solve for in number 13? What do we solve for? The direction of the force. If there's a force, then there's a, or I should say, then there's an acceleration. So it's accelerated motion both ways. Gravity is pulling it down. The electric force is pushing it sideways. There's accelerated motion both ways. 14 is B. Electrostatic force acting on a positive particle at point P. There's a force of repulsion caused by this one. And there's a force of repulsion caused by this one. Is this one bigger or the same or smaller? Tell me when to stop drawing it. Okay, I'm not sure if it's that much bigger, but might be. It is bigger. And we know it's bigger because, well, the charges are the same, but it's bigger because it is, Quinn? Yeah, it's closer, right? Since my distance is only r as opposed to 2r, my force is going to end up being bigger. So that looks like the answer is going to be C as a result there. Sorry, that was 15, wasn't it? Yeah. Okay, it's still C. 16. Oh, that's the one that we didn't count, right? Because it was a repeat of number 1. Oh, there's a good one. Oh, that's a great one. That is a great question. Boy, I should have saved that for your test. Two small spheres with charges qx and qy are separated by a distance r, and they have a force F between them. And then we make some changes. Or we double one of the charges, or quadruple one of the charges, or we cut the distance by a factor of 4 or something. We make 4 sets of changes. We want to find a combination that would maintain the value of F. In other words, this is my original force. I want to find a combination that will give me a new force that's the same. So let's try that, starting with the first one. If I'm doing the first one, F new would be K times 2Q1 times 2Q2 over 4r squared. That becomes 2 times 2 is 4 over 16 times my original 4. Does that maintain the same value? No. So let's take a look at the second one here now. You're right, it's not, but let's just go through it anyways. I know you don't want to. KQ1, Q2, KQ1 times a quarter Q2 over a quarter. Oh, this is definitely not going to work. Gives me a quarter over 1/16. Okay, that's nowhere close to being the same value. That's 4, right? It becomes 4 times my original, which is wrong. If I'm trying the third one, my new force is K times Q1 times 4Q2 over 1/2 R. This is looking more promising. 4 over 1/4. Oh, wait, no, it's not. Because 4 over 1/4 is 16, right? 16 times my original force, which is wrong. So the answer is going to have to be D, but let's just double check that. My new force is K times, what is it? 4Q1 times Q2 over 2R squared becomes 4 over 4 times my original force. The answer is D. Listen, guys, I don't know if this is a particularly great strategy or whether how often this happens. I don't have numbers for this, but anecdotally, I can say that, man, it sure seems like when I have to go through 4 options to check, it always ends up being like one of the last couple. So if I see this question on a test, I might actually start with D and go backwards. Because it really does seem like it's C or D more often than it's A or B in one of those. It's like they want you to do all the calculations, so they make the answer C or D. No guarantees of that, right? But it might be worth starting at D. What's the worst that happens if you start with D? The answer is A, right? It's like, oh, that was crappy advice. But you got all the time in the world now to write it, so it doesn't really matter, right? All right, 18. That's a good question. Which of the following conclusions comparing either the charges present on Y and Z or the masses is supported? Yep. Yep. What do we know about the charges? Well, we know they got to be opposite charges, right? To attract. Or one of them maybe is neutral. Do we know anything about the magnitudes? Like which one has a bigger charge? Not at all. The force on, like if the charges are the same, the force on Y is the same as the force on Z. If the charges are different, the force on Y is the same as the force on Z. The amount of charge will determine how much the force is, but the force is going to be the same on both of them, regardless of the charges, right? So it's not the charges that affect the amount of deflection, rather it's going to be the mass. Which one has more mass, Y or Z? What is it? It's going to be Y, and how do you, why is it Y? Yeah, more mass because it causes more gravity, which causes it to resist that attractive force more. So we're going to say sphere Y has more mass, and therefore it's deflected less. So 18 is C. And 19, we are so close. Oh, look, the nature of charge on sphere Z must be, if Y is positive, then sphere Z, if Y is positive, then sphere Z must be what? Definitely not positive. It's got to be negative to attract or neutral. Positive will attract negative or neutral. What did I say, negative or neutral? D. $20. Just a couple more questions here, guys. 20. Force versus what? Force versus the position. Force versus the position. We addressed this earlier, right? What's the force? How does the force change as it goes anywhere in between these plates? It doesn't. So what's the answer to this then? What's the answer? D. Force doesn't change with distance. $21. Second to last question. We're done. You got an ice pick that has an external electric field that points to the left. There's electrons in this ice pick. Shaylin, if I've got a positive particle in a field to the left, which way would the positive particles go? That is, positive particles that could move, not protons within a solid, but some kind of positive particle that could move. Which way would they go? Right, because I'm positive, the force is with the field. But if it's negative, they're going to go against the field. So the field is to the left, the force is to the right, and they'll therefore collect where? Yes, because they're being pushed to X. Right, a high concentration at X because it's a tip, right, a pointy thing. And the answer was, what did I say? The answer is C, yeah. And finally, this is it. Oh, is there one more after that? Oh. So when you get excited, there's more to go. I'm lying to you. It says, which of the following graphs represents the relationship between electric field strength and distance from a point charge? What do we know about that field in terms of uniform, non-uniform? Goes like this, right? That's a non-uniform field. And how do we describe that field mathematically? We've got three equations. Which one do we use to describe it? Yeah. E is equal to K, not KQ1, Q2, but KQ over R squared. Okay, so if we plotted that graph, E versus R, we would end up with a graph that looks like this. E versus R would look like this. Well, all four of these are straight. So how do we straighten it? We know that B can't be the answer, right? Because E versus R gives us this. But one of the other ones could be. How do you straighten that curved line? We basically did this in your Coulomb's law lab, right? Yeah, you got to plot a graph of E versus 1 over R squared. Why 1 over R squared? Because the equation is KQ over R squared. That's going to give us a straight line. The answer ends up being D for 22. And last one. What's the magnitude of the field caused by charge B? So listen, what are we really looking for here? We're looking for the y component here, right? The y component is caused by B. Let's get the y component. Let's do that by saying, let's redraw it, just make it bigger here. 71.3, 0.47. Let's say sine 71.3 is equal to opposite over hypotenuse. And that ends up being C C, 0.45 newtons per coulomb. 0.47 times 71.3 gives me 0.45.